All right, now we've looked at electric field, and we've seen that from a positive charge, we have an electric field emanating out, and that the electric field direction is the direction a positive charge would experience a force. What force am I talking about? Oh, this is the force I'm talking about. That's one of your equations, F equals EQ. So what they're saying is that this field here has a number to it. It has a strength at that point. And that if you want to know the force experienced by a charge, then all you do is you multiply the field's strength times the charge itself, and that will give you the force in newtons. Right? Simple as that. The only thing is, you need to know the field strength. Now, these fields are getting weaker and weaker as they get away from the charge. So those ones are a little bit tricky to deal with. But the old capacitor, that's what we often come up with in level 2. When it is charged, capacitors aren't always charged, they have to be hooked up. We'd have to hook this one up to a battery with a plus there and a minus there. That's how we'd hook it up, and it'll become charged. We can draw the field in here, and we can now work out its, if we know it's, we need to know another formula to work out the E, right? And that formula is this, V equals E D. All right, now if I've got 1000 volts here, and if I've got 5 millimeters here, I can work out the charge, can't I? Volts divided by D over here equal E. So volts 1000 divided by 5 millimeters. And remember, we always work in SI units, so that's 1000. I might as well do this way. 1000 divided by 5 millimeters. I just go exponent minus 3. I divide by 1000 to convert millimeters into meters, because this is in meters. And we end up with a value of 200,000. 200,000 volts per meter. That's E. So now we've got E, and E through here is the same through the whole, so it's called uniform. It's not like E near the plus is bigger than we're in the middle or near the negative or anything like that. So now if I want to know the force on a charge, let's throw a little charge in there. Doesn't matter where. What charge should we use? We'll use charge on electron. 1.6 times 10 to the minus 19 coulombs minus. That's the charge on an electron. So the force on the electron in there would be equal to E, 200,000, times the charge. And we can do that on our calculator. 200,000 times 1.6 exponent minus 19. And we've got 3.2 times 10 to the minus 14 newtons. So when a charge is in a electric field, it experiences a force. Now, if that little positive was in here somewhere, what it's going to get is a force acting on it. Now, since I said that was a negative charge, so put a little negative there, the force is going to be which way? Well, it's going to be up. It's going to be away from the negatives and towards the positives. Now, so that's electric force. This brings me to just discuss briefly work. And we'll do a few energy calculations. We just do this because we'll do that in another video. But work equals force times distance. Remember that one? Also, when you've got the ground here, you've got an object, and you lift that object up, you do work. And that work is equal to the change in potential energy, or mgh, right? The point I want to make here is that which way was the force going? Well, the force is going that way. Which way was the gain in potential energy? Well, as you went up, then potential energy increased. So when you go against the force, you have a positive increase in potential energy. Against the force, we get a positive increase in potential energy. So back to our little diagram. If I'm going with the force, which in this case is towards the positives with my electron, that would be a negative change in potential energy. I would have to push this electron towards the negative plate to have a positive increase in potential energy. Alright, so I think that's enough.